Let's do some elliptic trigonometry. The problems 13 through 16 on the week 15 wiki are going to be the kind that I'm going to try to do first. And this one is not on the wiki, but it's like them. We're starting out with a regular elliptic triangle. All the sides are the same size, all the angles are the same size. I'm choosing the 120. So if you know your stuff, this is a Reuleaux triangle. So what is the length of a side of a Reuleaux triangle? We have one formula. It's in the book, and it looks like this. If we apply that formula to the triangle ABC, you have to have a little a for a side and a big A for an angle. Let's talk about that for a second. Why would we have cosines of sides? Well, if you look at this triangle, these sides, the sides of the triangle, are circular arcs. They're arcs on circles. So to ask for the cosine of little side A is the cosine of this circular arc. Well, a circular arc has radians. So that's not the arc length, but the radians for that piece of arc. That's what we're talking about. So we're going to find the radian length for each of these sides of the triangle. That's what we're looking for in this formula. So we have the the formula with the things put in, but since it's a regular triangle, little a equals little b equals little c. So the formula immediately simplifies to this line here. And we know that the angle A is the 2 pi over 3, or 120, whatever you want to call it. The cosine of 120 is a negative 1/2. So if you look down here, I've got this line. That's the crucial line right there, because I've got all the cosines are cosine of little a. Cosine little b, cosine little c, they became cosine little a. Then I did this substitution. Sine of little a squared is equal to 1 minus the cosine of little a squared. So now I've rewritten in this line, the only variable is cosine of little a. Now it's squared, and I have a cosine of a to the first, but that's okay, because that's like my one variable, but it's in a quadratic. So what I did was I multiplied through, got everything together, combined the like terms, and I get a 3/2 cosine squared little a, because I have cosine squared a plus 1/2 more, because it's negative on the 1/2 here. So 3/2 of the cosine squared, then minus cosine a, bringing it over from the other side of the equal sign, and this negative 1/2 times 1 lives. So I multiplied through by positive 2. So I lost the two fractions. I've got this thing, which actually factors. You can see by the nice answers that I get from quadratic formula. But anyway, you guys will have to do quadratic formula on most of the ones that are on the wiki. I think all 3. You're not going to get the nicest answers in the world. But do the quadratic formula. Here's what it looks like. In my case, I actually get nice numbers, but it doesn't matter, because what I have is cosine of little a equals a 1. But the only way cosine is 1 is if a is 0. The cosine of 0 is 1. Well, that's not much of a triangle, is it? If each side is of length 0, that's no use. But this other answer over here is quite interesting. This one's okay, because I have cosine of little a equals negative 1/3. Inverse cosine negative 1/3 in radian mode or in degree mode. Now that 109.5 degrees is kind of interesting. Let's go back to the Reuleaux triangle. We're finding the 109 doesn't make sense as 109. It's just an arc. So that the other answer, the 1.9, this answer is the one that makes sense. That's the elliptic length of that side of the Reuleaux triangle. That's the elliptic length of one of these. So whatever that is, 1.916 radians. That's its elliptic length. Actually, it's best just to say it as 1.916. All right, so one other quick elliptic trig problem for you, and this one's simpler. I hope you kind of like this one. what I've done is I've focused on just the upper half of the disk, and I've made a triangle with a vertex at O and a vertex up at 12 o'clock called it point A, and then down here, so there's an elliptic line coming through, and I made sure to have the center for this elliptic line to be on this diameter. So I get a 90-degree angle here, and I always have a 90 degree with the crosshairs here. So I have a 90-90 something triangle. And I'd like to know what's the relationship between angle A up here and the length little a down here. And a funny thing happens because of these two 90-degree angles. When I use the only formula I have for lengths in elliptic, I end up with 90s for all the angles except for little a and big A. Or think of it this way. This is an arc of a circle, little a is. And big A is a regular old angle. So the cosine of 90 is 0. Sine of 90 is 1. So these two sine of 90s become 1s. And I end up with cosine of little a equals cosine of big A. Now let's understand why that makes sense to us. When you have a triangle in this very special position, each of these segments coming down, each of these elliptic segments has the same length. Their elliptic length is always pi over 2. This is a fact. You can solve it by doing this formula for a triangle that has a side here and a side here and a side here, and solve another triangle for here. You will get the pi over 2s. They really are. Those if you do the formula for these two sides. Another way to look at it that they have to be the same is that, look, I've got two 90-degree angles. This is an isosceles triangle. It's an elliptic isosceles triangle. So these two sides have to be the same length. Another way to think about it is if you had a whole globe, if you had a whole circular globe, you know, geez, where can I get a globe from? Oh, here's one. So if I had a whole circular globe, and the radius was 1, if the radius was 1, then I could say the circumference is 2 pi. And this much, or this much, you know, it's a quarter of a circumference. So it's pi over 2. That's what that length is. So we've got a way of getting this pi over 2 several different ways. That's the elliptic length. But notice in this formula, I never even used these sides. I calculated and found that cosine of little a is equal to cosine of big A. So in a sense, this length as an arc is equal to this angle in radians. A very special situation. I don't know if you'd ever need it, but it's kind of nifty how that formula works out when you got two 90s. It's so nice that it could come up. All right, you guys, I love it when you pop by the office and visit with me and we talk about geometry. It sometimes helps. I've seen people come in the office and we talk for a few minutes and they go back to the wiki and they understand and they're able to get their points. So use me. Let's get these last 2 weeks done and get them done fast because I know you got big work to do in your other classes. See you later.